And I'm gonna share the screen. Okay, so today we're gonna start with chapter 3. So let me know if there is any issues with sound or video. Everyone can see the screen, so I'm just gonna eliminate this outline so you can see better. I'm just gonna put this here so the recording does a better job. Okay. Mm-hmm. Okay. So please ask any question that you have. Right now, I'm not gonna see you on video because the recording the other day was blocking some of the um, of the text, right? So just open the microphone and tell me. So today is chapter 3. So chapter 2 was about basically reveal preferences and Slotsky matrices, comparative statics. So there is a section of chapter 2 that I'm gonna cover at the end of this class if we have time, which is about an application. So this is going to connect to the problem set. So the problem set solutions are already uploaded, so you can check and double check what you did. I will do that. I'm going to discuss a little bit about that later, but this problem set was super simple and it's more algebraic. So all of the things that we did in the problem set are super basic. Okay, so before starting, let me know if you have any question. I received a question by email about lexicographic preferences, so I'm not gonna answer that still because I'm gonna send a problem set about that. So yeah, in general, there are some questions that I'm gonna solve eventually as we reach the particular topic. So we're gonna get back to that at a particular point. Okay, just let me change something here. And then, I'm just putting I'm just using my other screen so I can see all you. You can see my screen, right? Okay, so now let's start. So this chapter is basically traditional consumer theory. We're going to study utility maximization, okay? The traditional approach, what we mean by that is we actually try to understand how to model consumer behavior through this paradigm of utility maximization, which in terms of rankings, it means that we have a consumer, a decision maker that is at the same time transitive and complete, okay? And basically the idea is that the consumer has well-defined preferences over all possible alternatives. So the consumer knows what they like, so they can rank any possible pair. And in particular, they also have this form of consistency. So in this form of consistency means that you can pretty much have this, you can be called intelligent agents. And we're gonna qualify by that, what we mean by that. So this is an interesting approach to modeling behavior. I'm gonna ask you a simple question before getting into rational preferences. So imagine, for instance, you're trying to model why people join a strike or a protest behavior, right? So what will you do? So I'm going to tell you two potential approaches, right? One approach, more sociological, if you want, there are some models of protest in sociology. We'll say that, you know, any agent has some probability of joining a protest, and they have some value that is, you know, how likely they are to join this protest, and then there is a threshold, right? And this threshold, if you're above this, you participate in the protest, and then if you're below that, you don't. So this is kind of the cost of joining the protest, right? Do you agree? So do you understand? So this is very simple. And then what you do basically is a model where this threshold depends on the number of people that already joined the protest and any time period, right? So this is decreasing. So the more people joins the protest, the lower is the threshold, right? So in a way, the cost is lower. Okay. So this model is in a way super simple, right? In the sense that you're not really maximizing anything, right? You're just comparing two things, right? So kind of the value of the protest versus the cost, right? And then whenever you pass the threshold, then you're done. And this threshold really depends on this rule of thumb of how much people join the protest already. Okay? So this model is a model where basically you're studying something very close to a zero intelligence behavior, right? So you are pretty much reacting in terms of some heuristic. Okay? So now compare this to a model of utility maximization, right? Where basically the consumer has to decide now whether to join a protest or not on the basis of some maximization process. So the first thing you have to do there is to define what is the problem, right? So in particular, what do you want to maximize? So there should be some utility, right, of joining the protest versus the opportunity cost of not joining the protest, right? So that in a way is a little bit more similar to the threshold, but here we're writing down a utility function that depends on each individual, right? And now this particular thing has to have some sort of budget, okay? So that means, how costly is actually to move to the protest site, and you have also the probability of being arrested, for instance, right? What is in general the expected benefit? Now you have to think about expectations, you have to think about beliefs, you have to think about time constraint, maybe transportation constraints, right? So what is the difference in these two approaches, right? As we get closer to Econ and to our framework, you are pretty much moving the load of the modeling to individual behavior. So you really want to model as much detail as you can the motivations of an individual, right? And so in particular, we are getting closer to a fully intelligent agent as opposed to a more zero intelligence agent. So now let's even go to another example, which is known for so segregation, right? So this is a famous model, Schelling. He was a Nobel Prize as well, right? So Thomas Schelling created a model of segregation. So the question is, why neighborhoods in the US are racially segregated? Okay, so, it seems like a hard question, and it is a hard question. But Schelling proposed kind of a very simplified answer, a very clean one, that at least explains some of the empirical facts. So let's think what he said. Let's understand what he said. So he proposed a zero intelligent agents, pretty much, where any neighborhood is composed of a grid of individuals, right? Where each entry of this grid is an individual of color blue or red, right? So there are two races, blue and red. Now, these agents are not that smart. They only have a slight preferences. So they slightly like more to be close to the same color than to the opposite color. So they have a simple heuristic, and they look around. So they're in the grid, and they look around to the neighbors, right? So think about a grid, a very simple grid. So you have some point in the middle. How many neighbors do you have, right? So you're going to have it's pretty much 4 neighbors that are adjacent to you, and then some diagonal ones, 4 more, right? So you have these 8 total neighbors. Now, from this, you like slightly more to be close to your own color. So that means that if you are blue, and you have 5 neighbors that are blue as well, you stay put, okay? So 5 is a little bit more than half, right? In the 8 total neighbors. So you have 5 or more neighbors of your own color, blue, you stay put, okay? You don't move. Now, if you have less than 5, then you move at random to other open position in the grid, okay? And then you check again, you see whether people are of your same color, at least the majority, so just one item is enough, the threshold, and then else you move, right? And so how does the model works? Well, you visit at random the grid and you update the state of the agent by basically checking the neighborhood, checking the number of the same color, and if it's above the threshold, so the number of people of the other color are more than half, then you move to a random position. So this is zero intelligence, right? I'm not specifying where they move. They don't move like planning. They are not planning to move to a new neighborhood, right? They just check this simple rule of thumb. They are not really computing, you know, they slightly have this homophily kind of preference, but nothing more, right? So this model actually, in very few steps, predicts that neighborhoods get super segregated. So you get clusters of blue, cluster of red, okay? And that's a very cool model of segregation because it's a very simple force that makes everything fully segregated, okay? So, so now, how would you think urban economist is thinking about segregation, right? So now there is a lot of questions, right? So how do you model the preferences of living in a certain location, right? So in particular, models of preferences for location are usually called hedonic models, right? And now you have to kind of infer the value of the location, trying to introduce things such as how good the schools are, right? How far are you from downtown, like supposedly good services and entertainment? And how far are you from work, commuting costs, right? Cost of the land, amenities, pollution, right? It's a huge amount of vectors. And then you also have this, maybe you have also maybe in your preferences, you are racist, right? How do you model that, right? So what is discrimination in econ? There are many models of discrimination. The one that we usually call discrimination is basically, so in lay terms, discrimination is basically a term in the utility, right? You dislike to be close to people that are not of your identity, right? So now, however, that's not the only type of discrimination in econ. One famous one is introduced by Arrow, right? Another Nobel Prize, which is called statistical discrimination, right? So they say, oh, look, maybe these people are not aligned with my preferences. And there is a probability, you know, that this person, so it's not for sure, right? But I just have a statistical probability. So most people of this other color, blue and red, right, are not like me. So therefore there might be some misalignment in terms of allocation of public resources and so on. So therefore I rationally can expect, right, that if I move this place, I will be closer to the public provision of goods and type of goods that I like, right? That's a kind of different explanation. So there are many, many layers that an economist can build, right? So as you can see, this gets more complex depending on your question. So which approach is correct? So right now I'm just gonna ask you, right? So let's fix the particular model of the protest, right? And then which approach do you think is better? So the sociological one or a more kind of rational expectations approach from econ? So I described this very briefly, so I'm not expecting you to be a specialist. So just tell me which are kind of pros and cons of modeling this in different ways. And also tell me if you see the difference. So go ahead, basically. Tyler, what do you think?
I think the sociological one, a benefit of the sociological one is you won't need as much data to model general results.
But that's a good point, right? Mm-hmm. But you see the difference, right? So one, in a way, right, is more systematic. So you're almost modeling agents as particles, right? So if you're an engineer, right, and you're faced with a problem, you know, so why there is an accumulation of of birds, right? Why do they behave in a swarm-like behavior, right? You don't need to model really fully the intelligence of birds, right? You have some systematic rule of thumbs, right? Do you understand? So this is similar to that. And now, of course, this is a more stylized model, so therefore you don't need as much data because you basically need the current state of the world, right? It's a differential equation, right? So you have the state of the world at time t, you know, this changes the threshold, right? And then you have kind of a bang solution. So basically, if you're above the threshold, then you join, right? Else you don't. And then you have these systems moving, right? And then eventually, you know, if there you have enough initial conditions in the protest, right? And enough benefit of joining the protest, then you have a huge protest, right? And then, you know, seems to be a good model. So I think that's a good example, in fact, that the sociological model is actually the better model to do, because we're actually modeling, you know, herd behavior. So in a protest, it's not that people are being super rational anyway. At least I believe in most protests is that way, right? is actually a collective phenomenon. Okay, so yeah, I mean, now let's think of the second one, racial segregation in neighborhoods. Do you think which model do you like, and what is your opinion on that? I described this very roughly, but an economic approach versus a more systematic sociological approach, if you want. So let's see, Tyson.
So systematic approach might be better because for if that's not the case, then you might have more subjectivity in the study. So that's my thought.
I mean, all models are wrong and subjective, right? So then you test it in data, and then you see whether they conform to reality, to the objective reality. That's why we have empirics, right? But at the theoretical model, all of them are conjectures, right? So they come from the mind of theories that are subjective in that sense. But okay, but I just want to point out one difference. So do you realize that moving houses is actually a very high stakes decision? Do people just wake up one day and then just move randomly to another house? No, right? Maybe in the prehistory, right? When we moved caves, right? But not now. I mean, you have to search, you have to make an effort, you have to actually think. Okay, so this is a more intelligent action, in the sense that you actually have to evaluate many scenarios and so on, right? So very few people, I think, will move randomly just because they can afford it. Even rich people, I don't think they just do it, right? I think most people will have to put a lot of thought in moving, okay, and a lot of time and effort. So you see, just from the type of actions that you are modeling, I think is a good rule of thumb to see what is the good approach. So like in things that you have to move fast, right? Like for example, a protest, right? It's gonna happen today at 4 p.m., right? You join it or not, right? There is no other shot, right? It's a fast decision. You are emotional because something happened, right? You're angry, you're happy, you want to do something, right? You want to be part of the group. So that's different kind of decision. But moving houses, I mean, you are sitting down, you are searching your options, you're creating your choices. You're saying these are the potential places I can move, including staying in my current location. This is the money I have. This is the loans I can get. These are the interest rates. This is the school quality. These are the rankings for workability. This is the rankings for criminality. This is the rankings for so and so. I visit the house in the open house. I try to check the neighborhoods. I try to check, many things. Okay. So this is very, very rational decision, right? So Schelling, because of that and many other models, won the Nobel Prize. And I mean, clearly he did something interesting there, because he reduced a complex phenomenon to kind of a simple idea. But maybe it's too simple, right? So the question is, what I'm missing there, is it really realistic that people move randomly to other locations? Maybe it's a good model of segregation in a room, right? So for instance, when we were live at Western, so we had seminars, right? And for some reason, the right wing of the room was always with the professors, and the left wing was with the students. Why? There was no sign telling them, sit next to the students, right? The left is the student wing. Not really, right? People came randomly, they watched quickly the room, and then they sat whenever they feel like it, possibly trying to be close to those like them, in the sense of being professor versus student, right? So Schelling theirs work perfectly, right? so just, focus on these small gatherings, also to remind better times. But I mean, in the end, you will see this Schelling logic, they're working very nicely, right? But for housing, I mean, there are so many things, even discrimination in terms of landlords, right? For instance, if people are trying to move renting, not even buying, like, that some people just won't rent you if you are not of the particular color, right? I'm a brown person. I have an accent. When I went to grad school, I called and you have to explain, you have to say many times, I am a student, you know. So yeah, so they treat you a bit better. So sometimes they just don't rent you, right? So I mean, it's not even my decision in that case, right? So in that sense, you know, these social phenomena are very complex to model. But I think the merit of econ is recognizing that there is a lot of stake and a lot of thinking in decisions. And that's very important. That's what makes us different. Because for instance, if you're a physicist, you know, you're a scientist, an engineer, most of the problems you approach are from a systemic point of view, right? So there is no thinking particles, right? In that sense, right? So you don't model the atom too much. You model the forces of the system, right? So in econ, we have both, which is hard, you know, but at least in micro, I'm gonna simplify the life for you. So the system is gonna be kind of muted because we're not gonna have interaction, we're not gonna have complex forces coming from the outside, right? You're gonna have the way I want you to think about this problem is someone sitting in a laboratory, so sitting in front of the computer, without cold, without being too warm, without being too hungry, you know, just with a clear mind, trying to make the best decision they can with a lot of information, okay? And when actually the decision matters in terms of money, so they actually make an effort of this decision, okay? This is now what I want you to start from. This is our benchmark. So this is kind of this isolated situation where I'm actually thinking a lot about my decision, okay? So I'm gonna proceed. So in this setup, right, as I mentioned, so at some point, decision-making theories decided that rationality means completeness and transitivity. That's the beauty of math. So centuries of philosophical discussion were reduced to two nice properties, which have a lot of information, right? As I mentioned, completeness means that you can compare anything, right? So you have a full rank, you can classify any pair of items they were given. And transitivity is this consistency condition, right? And then we basically define rationality as being any binary relation that is defined on a choice at X, in a grand choice at X, that is actually complete and transitive. And that, according to this dictionary, we said in the first chapter, this is called a total pre-order, right? So why is a pre-order? Because things are not ranked strictly, so there is some indifferences. So it's not gonna be a linear order, right? It's a pre-order. So still some things are not ordered because they are in indifference relation. So what is order is the indifference class, right? The equivalence classes. So this is already just language, but rationality means you are complete and transitive. So complete and transitive equivalent to total pre-order, okay? Simple vocabulary footnote. Okay, so now let's read some things that we're gonna say again and again in the class. So when I write X, this symbol, which is the symbol of preferences, Y, so I'm gonna just say X is at least as good as Y, okay? So this means basically that X is preferred to Y. So I'm gonna make the difference of the default is preferred is weak preference. So it can be that you're indifferent or you're strictly preferred, okay? And then I'm gonna say explicitly that you are strictly preferred. So whenever I say strict is actually explicit, right? Now, any preference relation happens to have two parts, right? So the first part is what is called the this is actually the asymmetric part, the asymmetric part, not the antisymmetric part. Well, the name is almost the same. Asymmetric part of this preference relation is this symbol that doesn't have the squiggle at the bottom. And in particular, this is defined as telling you that this is the strict part of the preference order. So I'm gonna define it here so you don't have to go back and forth to the previous part. So I'm just gonna do this. I'm gonna update this to make it simpler. So the asymmetric part of this is this symbol, and this is defined as follows. So we say that X is in a strict relation with Y, right? If and only if X is in relation with Y, but no Y is in relation with X. Okay, do you understand? So remember, what are preferences? They are ordered pairs, right? So in this collection of ordered pairs, you have that X and Y is in the collection, but Y and X is not. Understood? Okay. This is like the father to son relation, right? So just one direction. So a directed arrow. Got it? And then we have the indifference relation, which now says, I'm going to write it again. In this parenthesis in the updated notes, we say that X is indifferent to Y if and only if X is in relation with Y and Y is in relation with X. Okay? So now this happens to contain, so the preference relation has the two items now. So the order pair XY and YX. Do you understand? So I am sure you understand the informal version, right? Everyone understands. Strict preferences, indifference, very simple, right? What I'm trying you to understand on top is the mathematical definition, right? So that's the only stop I'm making. So everyone is on board, easy, right? So one, it contains the two ordered pairs, indifference, and the one only contains one ordered pair, but never the other, right? Okay. So I'm going to introduce some important sets that I'm going to use in proofs and to define properties. So the first one is called the upper contour set. Very nice name, right? But it's just the set of things that are better in the weak sense than any fixed bundle. So fix the bundle X, okay? And now you define the upper contour set, or capital V because it's best, right? It's better for this preference as all the items Y in X such that Y are in the preference relation with X. So they are preferred to X. Easy, right? So these are items that are weakly better, okay? Lower contour set, analogously defined, has an L name, okay? And this is all the Y's that are dominated by X. Okay, so they are, X is preferred to it, okay? Collection of them. And then this is a very well-known object, right? This is the object called the indifference set, okay? And this is the set of things that are in the equivalence class. So let's go quickly to the InVision. I'm just gonna share the screen so you don't need to get into the Blackboard yourselves. So let me share it to you. Okay. Today is slow, I don't know why. Well, but I'm just gonna pretty much do the pictorial representation of them. When this thing which was working is not working anymore. So, okay, we got it here. Okay, so I'm just gonna draw in, you see my InVision, right? Okay, good. So I have my diagram, right? And I'm just gonna write a bundle X, okay? And now what I'm gonna do is write down the indifference curve, right? So this is for a preference relation. This is the set of items that is basically indifferent to Y. So in particular, for instance, X and Y are indifferent, okay? So what I define like the I set is just the indifference curve. Now, of course, I can draw it for 2 dimensions, right? But for multiple dimensions, it's a surface for 3. For 4, it's just a manifold, right? It's a very object of high dimension in general. So I can only draw it for this particular dimension. So what is the upper contour set? Well, I'm just gonna do these lines here, right? So this here is the upper contour set. Right? And the lower contour set, you can imagine it, right? So it's the lower part, okay? So as simple as that. So of course, this is a very simple description for 2 dimensions. And now we don't, it's very simple. Now, of course, we need the mathematical objects to describe the multidimensional cases, okay? So math works for that cases. Okay, and now I'm going to define some additional properties that I'm going to use. The first one is called monotonicity. And this one is super important because it's going to play a role whenever we're doing proper problems. So monotonicity says a preference relation is monotone whenever we say that X is strictly preferred to Y, whenever entry by entry, the entries of X are strictly greater than Y. And then we say it's strongly monotone if XL is weakly better than YL entries for all the goods, but at least there is some entries under which XL is strictly above, okay? So again, people get confused for some reason because they think strongly monotone is not the best naming. But the good thing about math is that, so the naming is just naming, right? So just focus on the definition. So strongly monotone just means that if two vectors are ranked and then some entries are better than the other strictly, then you declare the whole bundle better than the other, right? That's why it's strongly monotone. And then of course the other one means that if you are entry by entry better, then you are strictly preferred, okay? So in particular, right, so think about the lexicographic ordering. So lexicographic ordering, right, of course, it is monotone, right? But it's not strongly monotone. Do you agree? So why the lexicographic ordering is not strongly monotone? Can you give me a counterexample? So Hursana, maybe? So my question is very simple, is that take the lexicographic ordering. Do you remember the definition, right?
Yeah.
And my claim is the lexicographic ordering is monotone, but it's not strongly monotone, right?
So in a strongly monotone, we don't need all the entries to be strictly preferred, right?
Yeah. Like for instance, that's the key, right? So the problem with the lexicographic ordering because it fails to be strongly monotone is that, for instance, you can have items, right, that are in the second entry, right? You can have that. Okay, so let's think again. So you have lexicographic ordering, right? And in fact, this is, let's see if you are entry by entry bigger. No, actually it's strongly monotone. So don't worry, this is a particular case. So yeah, and this is a particular case where you actually are strongly monotone because given that you're lexicographic, if you're equal in all entries except one, right, that is the only one that's gonna be active. Okay,
Yeah.
that was the example. Okay, and so in particular, right, we have this monotonicity idea that more is better. So remember that this is the idea that we had in the scalar money order, right? But now this is translated to vectors. Now, what is the key thing I want you to realize? So preferences in more than one dimensions, they may be complete and transitive, right? But may fail to be monotone. Do you understand that? So for instance, you may violate the more is better, right? So actually, this is an additional property I have to impose, okay? So in more dimensions, these notions of more is better quickly get lost, right? So you need to impose it explicitly. That's basically the role of these assumptions that we're gonna have. So preferences that are strongly monotone are monotone, but not the other way around, right? So I'm gonna introduce now a even simpler property in the sense that it's even weaker than monotonicity, that it still gives you the idea of that more is better. But in this case, this is a local enunciation. So what these preferences look like? Well, I'm gonna draw it in a bit, but they tell you the following. Say, a preference relation satisfies local enunciation if for every x and every epsilon, there exists a point y such that the norm, this is an object from linear algebra calculus, right? So this is the distance between two vectors, okay? So if this norm is less than or equal than epsilon, and then it happens that y is strictly better than x. So I'm gonna draw it, but basically what you have to understand here is that being locally enunciated, is something that is weaker than monotonicity, right? So I'm gonna do this as usual, x2, x1, and then I'm gonna have this thing. So these kind of preferences that are not usual preferences, right? And preferences are going in this direction, right? So for instance, any item here is better than any item here. So x2 is strictly preferred to x1. Okay? So now, for instance, are these preferences locally non-satiated? Well, yeah, right? So for instance, take x1 and then draw any particular ball, right? In this case, I'm gonna do the Euclidean metric of what size epsilon, right? Okay, so 1 second. And then, okay, today this thing is weird. Okay, let me erase it. Okay, technology, wonderful. Okay, so now we have that in this ball, right? Any of these items are actually inside. So, okay, so let me do it here. I don't know what's going on with this. Okay. You have here the x1, this ball here of size epsilon. And now any item, there is an item here, y, that is better. Okay, that's the idea. So this one here, it doesn't even require that monotonicity holds, right? It just means that there is some small ball around x1 that you're better than the other, right? So these kind of preferences are more general than monotonicity. Okay, it just means that you actually are better. So another example of these preferences that are locally monotone but not monotone is preferences of this type. For instance, circular preferences, right? And then in this particular case, I'm gonna remove the satiation point, right? So there is no satiation point here. So for instance, if I take any x here, for instance, this epsilon ball here is gonna contain some better items. So these ones are growing to the middle, but I'm removing the midpoint, right? Which is, there is no satiation in this case, right? This is unaffordable to you. So in particular, this one, there is a y here in this epsilon ball that is better. So y is preferred to x. So I'm just telling you this in the sense that, as you can see, y and x are not necessarily ranked in the vector sense. So there are many more preferences that are not monotone that are actually locally non-associated. So again, why do we care about these things? So they are just now mathematical conditions that they are gonna come handy when I'm doing my utility maximization problem. So in most cases in real life, this will only come handy when trying to verify whether a problem has a solution and whether you can apply in theorems. So the way I want you to understand this thing is that we're not right now talking about something important in terms of behavior. So it's not that I can test in a laboratory whether a preference is locally non-associated. Do you understand that? Okay. So you understand that this is not really talking about an econ concept. So this is just the most general, more abstract condition that covers actually meaningful, interesting models that you can just verify easily mathematically, and then you can apply a set of theorems, right? So what is the purpose of this class for known theories, which is most of you, right? Is that you can invoke many of the results in this class or very similar results whenever you are doing a model for your particular necessity, right? So a lot of people in Western, they become what is called structural economists. So what an structural economist will do is you will write down a model, right, of behavior of an intelligent agent, a maximization usually of utility, subject to some particular constraint. And then the first thing you should do as a practitioner is that you have to verify that your problem is going to have a solution, right? That this solution will actually be unique, right? And then you actually will produce some sort of a consistent behavior. So in particular, in order to do that, you'll be able to apply some theorems from the class. And in order to check whether these terms apply, you want the terms to be stated in the most general way possible, okay? So that's why we're gonna learn at this level of generality, okay?
I have a question.
Sure.
Okay, so seems like all preference relation satisfies local non-saturation. Like, can you give an example of a preference relation which doesn't satisfy local non-saturation?
Yeah, of course. So let me do it. So you're seeing the screen, right?
Yes. Yes.
Okay. So imagine now that my indifference set is this surface, right? So these are thick indifference curves. So they, yeah. So you're ruling out that if you want into D. So there is no way of indecision if you want. Like all this area, you don't know what is good. Now, so that's an example, right? The classical one. Okay.
I just have.
Any other?
I just have a. Oh, sorry. Go ahead.
Sure, go.
Go ahead, please go ahead.
I just have a quick question. So, a preference relation, that is just like if the relation is complete, transitive, and continuous, or does it just have to be complete and transitive?
Continuity, we haven't used it yet. Continuity is gonna come later when we introduce utilities. So right now, continuity, we don't need it at this stage. I'm gonna define it in a way. So right now we're just talking about the most general model. Yeah, so continuity hasn't come into play. So they don't need to be continuous at this stage, but we're gonna need it when we introduce utility, okay?
Victor, can you give another example of not satisfying the local non-saturation, like other than this? Is there any other else?
I mean, there are many others, like for instance, the satiation point, right? Like for instance, you're saying, this is the target area, right? So this is a point, if you want. So this is the best item, and the rest of items are worse, right? Of course, this is someone that is super picky and just eats one slice of pizza. They don't like 2 slices. They don't like half a slice. They hate any other thing that is not 1 slice of pizza, right? Very picky eaters. So yeah, so this is the point that is the better object, right? This is the X star, satiation point, and the other items are worse, right? So of course, at this stage, at this particular point, anything outside it is worse. So that breaks also local non-satiation. So there is a point at which that the satiation point you cannot improve. Okay, so you're also ruling out that there is no satiation points here.
Yeah, thanks.
Okay, so let me share now my leaks. Good, so back to the leaks. Okay, everyone can see it? Okay, so now, by the way, guys, do you follow Econ Twitter? Who does it? Okay, there was a huge discussion, I think, a week ago about local non-satiation. Someone was complaining that there is too much math in Econ, and they were putting an example of this local non-satiation from Maskell. Well, it's one thing I want to clarify, right? So, you know, math is really a language, right? And I think, you know, do you think learning more languages is good? You know, I think it's great, right? So I personally, I learned math kind of. So I learned math as an economist first, but then I did an applied math master. And when I went to the applied math master and I spent 2-3 years just learning math and math and math, for me it was like learning another language, right? I learned French, I learned English, just opens your mind, right? So you can just express your ideas better. So knowing math is really about, you know, learning to express your ideas in econ in a new way. So for us, it's really the final objective is modeling, right? So it's not that so I want you to understand in that sense this. So in a way, you know, first year courses are very intense courses that try to see, you know, your grit, how much you can do, and they're pretty much trying to, it's a double matching problem, right? You're testing the waters to see if you like this profession, right? And also we're seeing whether, you know, you're gonna do well in the program. And that's actually important for happiness, right? So this is important to test the waters, but math is the language of economics. And the more you know, actually, it's gonna make you better at expressing your ideas. And I think that's the cool thing. So remember that, right? So all these things, you have to see it as a template of things you can actually learn. So it's more about the concepts, it's about the language. So I want you to think about this class as a modeling class, right? And we're gonna do more as we go through. So now I'm gonna just give you this quick thing of an example where basically the demand function is going to be the result of maximizing a locally non-associated preference on a budget constraint, right? Then you have to be on the budget line. Okay, so do you understand this? So Walras law is an implication of maximizing a preferences that is locally non-associated. Can you see this is true? So just intuitively, remember in the previous chapter, we just imposed Walras law, okay? We say out of nowhere, say, people are gonna choose on the budget line, okay? Now, instead, we're changing how we're modeling. We're saying, look, you have a preference relation, a preference that has a property, local non-association. If you maximize that preference, now it implies the Walras law. Do you see the difference, right? So now we went back, a step back, went to a primitive object that you cannot see, preferences, impose a property, that's modeling, right? Imposing properties on a latent object. And now I imply an empirical law, which is that you're gonna spend all your money. So now let's prove it. So the proof is there, right? But I want you to try to do it now mentally, right? And I'm gonna ask one of you, just think about how to prove that if you maximize a locally associated preference, then you can do it. So I'm gonna ask Showman.
Yes.
Or actually, Showman, wait a bit, maybe for the next one.
Okay.
Instead, I'm gonna ask Brice. Okay, so just prove that that maximizing a preference that is locally associated implies Walras law, so that you have to live in the budget line. The argument can be done verbally, right? So let's just start. I'm going to give you a hint, right? So the idea is that the easier way to prove this would be using contradiction, right? So assume towards contradiction that your bundle is the product of maximizing a utility, a preference function that is complete transitive and locally non-associated. However, you are not on the budget line, right? So you are below it, okay? You still have to be affordable. You cannot be above it, right? You only can be below it, strictly so, okay? So let's go to the screen, to the board. So what I'm telling you is this, right? So you have some preference relation, you have a budget line, right? EW, you have a preference relation, right? And however, your maximization point is here, right? This is the demand, which is below the budget line. And I'm assuming this is locally non-associated, right? So go for it, right? So is this possible?
This is not possible because if I choose a small radius, I will always find a bundle inside that is preferred than X.
Yeah, exactly. But you're missing a key point, right? So I take a small radius around it, right? And I can do it because, and this radius, because it's below the budget, right? Is gonna contain objects that are of the following form. So here there are gonna be objects, Y, that are two things. First, Y is gonna be better entry by entry than X, okay? Okay. So in particular, right, because monotonicity implies local association, it means that Y, you know, is actually strictly better than X, right? So now if you have an object, right, that is just better entry by entry than this, right? And so the object X, what was the assumption? That X was the maximum, right? So X was better than all Y. For all Y, right? In the budget, okay? So of course, if I'm finding an object in the budget that is better than X, then X is not the maximum, okay? Got it?
Yes.
So let's go back to the proof. the formal proof. So right now I did a graphical proof, if you want. So if a demand function X is the result of maximizing a locally non-associated preference on a budget set, then I have to be on the budget line, so Walras law. So again, what is the premise P? X is maximizing and affordable, right? Such that you are in the budget. And the preference is locally non-associated. What is Q is that you belong to the budget line, so Walras law. Now, I negate the statement, right? P and not Q, and this will prove that this gives me a contradiction. So P and not Q means that X is maximizing, affordable, and locally non-associated, but at the same time, you're below the budget, strictly so, right? So I just took the implication, P implies Q, negated it, which is P happens and the conclusion fails, right? That's the negation. So then, of course, there exists a radius of epsilon small enough such that there is a y in the budget line that is affordable inside this radius, and that is better, right? But if it's better and affordable, then it's the maximum, right? So it's just better than the X. So the X cannot be maximizing, because being maximizing means that there is nothing better, okay? Agree? So now, the cool thing about this, and this is the purpose of chapter 3, is that now we're going to start from preferences and then derive all the properties that we had in chapter 2. So the first one is done, Walras law. So now we need homogeneity, right? So, okay. So before going there, I need more properties. So this is a lot of definitions because these are the first classes. So one thing I'm going to use a lot is called convexity. So preferences are convex whenever I take X is better than Y and Z is better than Y, and then I take a convex combination of X and Z. What is a convex combination? I have a parameter T going from 0 to 1, and then I combine using this scalar T, the vector X and the vector Z, and the combination gives me a new vector, okay, which is the mixture of these two, according to parameter T. And this one has to still be better than Y, okay? If that happens, you are convex, okay? So can you draw it? Yeah, this is easy, right? So let's share the screen. Let's do it, right? I'm gonna draw something that is not convex, right? So this grows in this direction. So take this object here, this object here, right? X, Y, okay? And they're gonna be indifferent to this object Z here. They are all in indifference curve. Do you agree? Now take the convex combination with some parameter T of these objects here, right? And now my convex combination, which I call B, is below Z, right? So this is not convex, of course. So what is the key, like geometrical equivalent object of describing this? Is that the upper contour set is not convex in this case, right? So it's a not convex set. So really convexity of preferences means that the upper contour set is convex, okay? Everyone understands? So what does it mean in terms of behavior? So what does it mean that you like, that you have convex preferences? So some people say that people like more mixtures than the pure objects, right? So for instance, do you like orange juice? Who likes orange juice here? Who likes milk? And now who likes a shake of orange juice and milk? So less people, right? So you don't have convex preferences, but you see, so that's the idea. So you take mixtures, right? And then here you're assuming that you like mixtures better than the other, right? That's convexity, okay? So yeah, that's the object. Now, why do we care? So imagine I have this non-convex preference, right? And now I'm trying to maximize it. So I'm trying to maximize it. So then what happens? I have now suddenly 2 points that are maximums, right? So of course, if I have a strict convexity, I'm gonna have uniqueness, right? So lacking convexity is gonna give me issues with my model. Issues in the sense that I'm not gonna make a single prediction. So I'm gonna talk about that later. Okay, so let's go back to the leaks. So finally, utility, right? All this, so we're going in circles to tell you about utility, and then from now on until you die, you're gonna use utilities, right? Well, not so fast, right? So preferences are actually useful because preferences are way more general. So you can actually do way more with them. Now, utilities, of course, are the standard workhorse model, right? And this will actually be the main thing you use. I don't know what you will become, right? But why do we understand preferences? Because they actually allow us to understand, you know, the main behavioral implications. So with utility, it's harder to see what's going on. And that's why we have many languages in decision theory. But think of them as different layers of the same object. So utility representation. Preferences are the most general way to represent consumer tastes, as I said. However, they are not particularly easy to work with. So for instance, if you are modeling complex economic problems, you want to write down a model, right, that you can solve in a computer, maybe. So using ordinal objects is kind of hard, right? Maybe then we have breakthroughs in computer science that we can use the ordinal objects, but right now it's kind of hard, okay? So instead of that, we're gonna use now calculus. So we want to get back to calculus land. So I'm gonna introduce this utility mapping, which is a mapping going from the choices to the reals, okay? And then I'm gonna say that a utility function is a representation of a preference relation whenever u of A is greater than or equal to u of B if and only if A is preferred to B. So there is a lot of information here, okay? I want you to understand completely this. So what is if and only if? So let's ask Alexis. So what does it mean if and only if logically? Right, so can you read this alternatively? So can you explain to me what is if and only if?
The utility of A is preferred to the utility of B. It can only happen in the one case if A is preferred to B.
Okay, that's one direction, right? One arrow, right? So you can go the other way is if and only if. So you have two ways. So remember this, what you say is one arrow. So you said, if A is preferred to B, then, right, the one direction of the arrow is that utility of A is greater than B, the utility of B. Now the other direction of the arrow is if you're giving only the utility numbers, and you told me utility of A is greater than utility of B, I know for sure that in the preference world, A is ranked above B, okay? So I can go both ways. So what it means is that all the ordinal information that I have in preferences are captured by a utility function. Now, what is the trick, right? There is always a caveat. The caveat is that this only works for complete and transitive. Okay? So any other preferences that are not complete or transitive, you cannot use utilities. So what does it mean beyond the math? I mean, I told you that the whole thing about utility functions and completeness and transitive was reduction of dimensionality, right? So what I'm doing now is I'm taking vectors, right? Huge commodity bundles, portfolios of size 100, right? And then creating a number, right? Like Schumann said, I think, you said you can take the expected value of a portfolio, right? So you're projecting a big object into a number, okay? That's what the utilities do. So now, you know, I told you that I'm modeling an intelligent agent. Do you think intelligence can be modeled by a scalar object alone? So a utility, even is very complex, right? I can add, you know, what you like, what you fear, your hopes. Just kidding. No, but I mean, you can add a lot of things mathematically to an object, right? But in the end, it's one dimension, right? But a lot of problems are not one dimensional, right? Like think of, we're now in very hard times, very difficult times, right? So now we have to actually take more seriously even, you know, these models. So like how people actually try to understand a situation like COVID, right? So there is a lot of pieces of information, very hard to understand. So you have to evaluate the risk that you are facing. Do you know this probability, right? So can you write it down as a belief, right? It's something that you actually know. So how do you model uncertainty, right? It's a very hard problem, you see? So this is a lot of information thrown at you in one line, right? So we're telling you, look, we're gonna reduce intelligence of this agent to a single scalar object, right? So you can rank anything and make it completely scalar, right? So you're telling me any situation right now, and you tell me a number, right? So you know, for instance, that tomorrow going to a patio is better than staying at home, for sure. I mean, it might be good in some dimensions. It might be bad in other dimensions, right? You see, that's multidimensional. It's not, there is no clear answer. I don't think right now we have clear answers, you see? So that's an issue, right? So in most real life situations, problems are multi-attribute, right? Multiple utilities, not one. But we're going to start from this benchmark, which is the nice, clean one. And you will be surprised that all econ you know, most econ you know, structural econ, macro, all macro is done in terms of one utility. So this workhorse, so simple, so clean, is very powerful. It's like the Schelling model in a way, right? So it's Schelling on asteroids, you know? So in the sense, you know, and that's the magic of modeling. It's the simplest thing you can do to explain a phenomenon. Now, as phenomena get more complex, you know, and as we economists get more serious, because now we're getting pushed. Right? Now we have to show this in numbers. We have to calculate. We have to model this. We have to estimate this with data. We cannot just talk, right? That's the key, right? So data is gonna judge us. Data has become more important and more important. We have now data. We have experiments. So now, you know, the stakes are higher, right? So now maybe this model is not good enough. So this is what I want you to judge, right? So just don't take it for granted. So, but right now, what I'm giving you is a lot of information. I'm telling you, the moment you are complete and transitive, right? And for now, in this summer, I'm gonna prove it only for finite case. Now, in the main class, I'm gonna do the full-fledged, more mathematical general case for infinite consumption bundles, right? Which is mathematically important. But also is important because there are things like portfolios that you can potentially have the continuous, right? And in that case, there exists a continuous map in U that represents the preferences, okay? So let's prove it. So necessity, one direction of the arrow, if and only if. So if and only if is two ways. So necessity means that if there is a utility function U such that for any AV, U of A is greater than U of B, then A is preferred to B, okay? So I want to show that. So if there is a utility function U such that U of A is greater than U of B, then I declare a preference relation A better than B whenever this happens, okay? So what I did is I defined a binary relation using the numbers of the utility, right? So for instance, Shumen gave me an expected value. I said, okay, so if the expected value of this vector is bigger than the expected value of this other vector, I declared vector 1 being strictly preferred to vector 2, okay? Now, if that's the case, I want to just check that this preference that I define is complete and transitive. So this one is super fast, it's super easy. Why is complete and transitive? Well, basically, this follows from the fact that the utility is just a real number, right, in the real line. So the ordering of this real line is just the greater than equal ordering. And that ordering is already complete and transitive, okay? So it inherits completeness and transitivity from the scalar order. Got it? Okay, that one was easy. Let's go to the hard one. Sufficiency. Sufficiency is the other direction of the arrow. So if there is an ordering on X, pretty much that is rational, complete and transitive, then there exists a utility map in U such that if for any A and B that A is preferred to B, the utility of A is greater than the utility of B. So what I'm gonna do now is I'm gonna construct a utility function from the ordinal information. Do you see the difference? So now I go from preferences to utility. Good. So the thing I want to do is basically I want to construct this lower contour set of the preference relation. So fix any item X and then build a lower contour set. The lower contour set, as I mentioned before, is the set of all Y's such that Y is better than, such that X is better than Y. Okay, good. Now I give you a utility function. This one comes from my mind, right? I created it. I want it to be so. So it's not a step in the proof, right? And this utility is just the cardinality of this set. So how I came with this realization, right? It's not a magical thing. It's logic, right? However, it's not obvious. You say, how do I rank things numerically using just a ranking? Well, so imagine you take all your objects and then you imaginarily create this pyramid where the best things are at the top and then you keep descending, a ladder, right? So the top of the ladder is the best object, and then you go descending, right, in terms of the ranking. So then how do you assign a number to the first object if you want to rank it? You say, look, the higher object is going to be represented by the number of objects below it, okay? So just below it. So that's the lower contour set, right? If I count the number of objects below it, then of course, it's going to have properties of the utility function. I haven't verified it. This is just now a conjecture. So now I have to verify this is a utility function that is representing the preferences. So here comes a part that other years I kind of emphasize a bit more. It's a more mathematical thing. What I want to say here, I'm going to skip this particular part. You can read it for the more mathematical advanced students, is that this utility function is actually a well-defined utility. So this means that if I take any object in the indifference curve, I'm going to have the same number coming out of it, okay? So being well-defined in simple words means that a utility function will give me the same numerical value for any object in the indifference curve, okay? So all this part is telling me that. So I'm going to skip it right now. What I want to check basically is the following. I want to check that this is the part with pretty much indifference. And I want to prove that the second step is to prove that the particular construction represents the preference relation, okay? So if I have that A is preferred to B, it has to be that the cardinality of the lower contour set of A is greater than or equal than the cardinality of the contour set of B, okay? So let's prove it. So if A is better than C, then C belongs to the lower contour set of B, okay? By transitivity, right? So I am using transitivity here. Do you understand? Everyone is on this step. So the first thing is telling me, look, A is better than C, right? So that means C is in the lower contour set of A, right? But by transitivity, it means that also it has to be that C is in the lower contour set of B, okay? Because A is preferred to B. And now C belongs to this lower contour set of B, and then it has to be that B is better than C, okay?
Victor, I have a question. So C is a subset of the lower contour set of B, right?
Yeah, so let me do it again. There seems to be a typo here. So let's do it from scratch, okay? Okay, so I want to show this, okay? Now, I start with some object. So I want to show that the cardinality of the contour set A is greater than or equal than the cardinality of the lower contour set B, okay? So what I want to show, this is equivalent. This statement here is equivalent to saying that the lower contour set of A contains the lower contour set of B. So let me write it here. Okay, that's what I want to show. Do you understand that, right? So basically the bigger set has more items, will have the larger cardinality, okay? So in order to show this, I'm gonna use transitivity. So start with an object in the lower contour set of B. Okay? This means, of course, that V dominates this, okay? I also know by assumption that A is preferred to B, okay? Then by transitivity, and this is the key, what happens? A also dominates C, okay? Which implies that C belongs also to the lower contour set of A, okay? This is equivalent to this statement. I'm just repeating myself here, but it's fine. Okay, that's the proof, right? So, so important thing about here is that I need transitivity in order to show this, right? Without transitivity, you cannot show this, okay? So now, this means, of course, I can specialize it also for the strict part, right? Do you agree? So imagine you have the strict contour sets, and then basically, if you are strictly above, you're going to have at least one more element, right? And that's it. One thing that is surprising, have I used in this direction completeness? No, right? So what does it mean, right? So imagine now that I give you some preferences relation that are transitive but not complete. Okay. So then, is there a utility representation for that preference that is transitive but not complete?
I don't think so, right?
No.
Doing clearly, right? So I just stated an axiom saying you need to be complete and transitive in order to have a utility representation, right? But what you can have is this, and I'm gonna just tell you verbally, this is actually a problem set at some point, but I want to realize how you can use the proof, right? So if you have a preference relation that is only transitive, then it turns out that you can always construct a utility function from it, okay? But with a utility function, it's already complete and transitive, so you can never derive the preference information from that, right? So the key idea is that when you lose completeness, you actually have multiple utility representations, okay? Because in the area where people don't know what to do, you actually have a different utility representing that, right? So let's think about COVID, right? So COVID is a complex situation, right? And I don't know how to compare many situations because I don't have the information, right? It's hard to compare. So imagine, so how can I model that? So one model that is very popular is called multiple selves. So you have multiple personalities, right? A psychologist will say you're crazy, but economists say you're fine, right? So you have multiple utilities. And then with these multiple utilities, you have a cautious one and a more optimistic one, right? So everyone has that, right? So you're on an optimistic mood. You say, nothing's gonna happen. And you have a cautious one, you say, the worst is gonna happen, right? So, and then, you know, when you evaluate a situation, you can evaluate with these different rulers, right? Different measuring sticks, okay? So that's a way to actually evaluate situations. And that's an incomplete situation. Now, in this case, right, there might be points of agreement. So you say the cautious and the optimistic one agrees, right, that these two situations are obviously ranked, right? So using a mask is better than not using a mask, right? So that's obvious, should be. And then, you know, and just an example, but this obvious thing here, right, this is an agreement point between the two, right? And then if I have another agreement point, you know, then it has to imply that transitivity still holds. So the first point was better than the last point, right? So transitivity can hold without completeness. So, and this transitivity will hold in the set of agreements, but you have different measuring sticks, okay? So this is an example of how you can go very easily from the toy model that we're studying to a more complex model, right? By just relaxing any of the two axioms. So right now we drop mentally completeness, okay?
So Victor, you're telling, so the same preference relation, which is transitive but not complete, can have many utility representation for the same preference relation, right?
Yeah, and the key thing is, remember, so a utility gives you one measuring stick, right? So everything can be compared in a real line, right? But I'm telling you, like in situations like COVID, right? So because it's so complex, some situations are not easily ranked. So you don't know which one is above the other. So is it good to do it, right? Like for instance, say, you know, we have this dilemma every weekend, right? So a new friend tells you, you know, let's go to a patio. There is some risk, right? But you also need mental health, right? So you also want to see people, right? And so which situation is better? Staying at home or going to the patio?
Staying at home, yeah.
For you, right? But maybe you are now being cautious, but maybe you are optimistic or you want mental health. Maybe you want to go to the patio, right? You see? So there, I have two selves. That's why I say I have two measuring sticks in the incomplete sense, right? So I can have two ways of measuring. So that's what is completeness ruling out, right? So for instance, if you assume completeness, you cannot have the two selves. You have to commit to one, right? But in real life, you can have these complex situations. Do you understand? So what I'm telling you is that right now our model is this very simplified model where you have one measuring stick that always can measure, compare anything, and is transitive, right? But as models have progressed, you know, and they have progressed a lot, you can remove any of these two assumptions with a lot of new ways to model behavior. And I'm just telling you one way. So if you remove completeness, now you have multiple measuring sticks. And in the case of COVID, for instance, let's go back to the patio, going to the patio with friends or not on the weekend. If you're under the optimistic mode, you say, look, you know, I want to be happy, right? So a life is a life that if you want to have a life worth living for, right? So you want to go to the patio. And you know, that's the optimistic case. And if you are in the cautious case, you say, like, I can wait. Maybe 1 year, maybe 2 years, I can wait, right? That's the other one, right? But there is always gonna be some agreement points, right? Like saying a mask is better than no mask, right? And then, you know, you have another agreement point saying, look, it would be great to have a vaccine rather not to have a vaccine, right? And then you can use transitivity there and so on, right? So what I'm saying is you can have transitivity without completeness, okay? And this is actually a model that is very natural and is a model of multiple preferences, okay?
Can you have the other way around, like you're complete but not transitive?
Yeah. So being complete and non-transitive means that you can compare any two things, but then you kind of have these inconsistencies, right? For instance, you like the apple to the orange and the orange to the pineapple, but then suddenly you prefer the pineapple to the first fruit, right? And some people behave like that. That's an empirical question. People have found evidence against transitivity, right? So we're going to discuss that on time, but that's a more difficult one to do. But yeah, so the important thing is this. This model will work in many cases, but it's not the only thing people do, right? Let me put it like this. So by relaxing these conditions, you can actually get new models, and that's why preferences are more important in a way. But the utility function is the core, the workhorse model, okay? Good. So finally, continuity. And this is what I call a technical condition. So technical condition is an assumption that doesn't have behavioral content, right? So continuity means that if you have you have pretty much two bundles, xn and yn. This is a sequence of such bundles. And then if I take the limit of them, it follows that in the limit points also preserve the relation. So I'm going to tell you the following statement. Lexicographic preferences are not continuous. Okay, I know I'm correct. so lexicographic preferences are not continuous. So can you prove it? It's a hard proof, but so I'm not going to ask you to do it right now. Only if you know. So any one of you knows the proof?
Yeah, it's just like.
Yeah.
Okay, great. So tell me.
You can consider some sequence. Suppose it's like the 1 over n, it's a pair, but it's a sequence for n running from 1 to infinity. And you can let like yn be another sequence where it's just like a number, sorry, a pair 0, 1.
Exactly. Okay.
And then, yeah.
So let's do that, right? This is supposed to be an N, right? So don't think that my bad handwriting is just a matter of the tablet. It has always been bad. So that's why I type things, by the way. So, so this is not an issue of the computer. So this one, in terms of lexicographic preferences, right, it's gonna be better this object here, right? And I'm gonna put here, okay. Gonna go to 0, and it's gonna be, so, okay, this is better. Okay, let me change this one here.
Better to have one over n.
Yeah, thanks. So, okay. Boom. Yeah, so this one, for instance, here is gonna be, it's gonna give you that the first entry, okay, this one is better than this one, and then in the end, it's gonna converge, right? So this is another example. It's different from the usually I do. But this one is very simple. It does the purpose. So this one is sequence xn, and this one, of course, is y, is a constant sequence. And then I have that xn, you know, is strictly preferred to y for all n. Do you agree? Because in the lexicographic order, in general, right? So this will tell me that the second entry is better, right? Always. And then as I take the limit, right? Then of course we're gonna get indifference. But I have a better one with a flip, because this one goes from strict to indifference. So that one obviously is not continuous. That is not as surprising. So let me do another one. But this one you understand, right? So just in the limit you change preferences, right? You start from a strict, and therefore you jump to the indifference, right? So obviously the strict part is not continuous. It's not a continuous preference relation, okay? You understand? Because you're always above one n, and then suddenly in the limit you go to 0, right? So then you become indifferent, right? So this is of course discontinuous. Okay, everyone agrees? Yeah. So in general, right? Lexicographic preferences are not continuous, and this one is one example. There are others. I'm going to also give you one later in the notes. But the important thing here is that you need this continuity in order to be able to write down utility functions for cases of infinite data. So what is infinite data? Well, we already discussed infinite data. Remember that we were dealing with the reals. So we're Euclidean space, vector spaces, portfolios, right? So R2. R2 is continuous, right? Is a space that is not discrete. So therefore, you actually need a utility representation for those cases, not only for discrete cases, okay? So in this particular case, you cannot have utility representations if you don't have continuity, okay? And so if preferences are complete, transitive, and continuous, there exists a continuous mapping U such that U x greater than or equal than y, even only if x is better than y. The full proof is going to be done in the main class. Now, why I said that continuity is not a behavioral thing? So can you test continuity? Not really, right? Because you will need an infinite number of experiments, right? So in order to test continuity, you will need to ask a sequence of experiments, right? And then actually take it to infinity. So there is no way I can do that in real life. So in finite time, in real life, I can never test continuity, okay? So why do we care about continuity? Well, we care because we actually want mathematical objects that are well-defined, right? So, but what it means is we can do this assumption without loss of generality. So this is a fully technical assumption. So you say, but isn't it realistic that some people suddenly jump from liking to something to then not liking it? Maybe, but the problem is that empirically I can never know, right? Because this implies checking infinite amount of data. I can never see these discrete jumps. I can never see it because I can always fill in the blank. You're never going to have full experiments, right? So I can always make it continuous. Do you understand what I'm saying? So even if you can visualize this in your mind, you can never test it in real life. Do you agree? Do you understand why continuity is just without loss of generality, right? So this is a technical assumption. So implication, it means you can never know whether an agent has lexicographic preferences or not, okay? So you can never know whether it's lexicographic. It turns out that I can always write down a non-lexicographic preference that actually represents lexicographic orderings. So it gives you the same demand. You will never know. So there is no way to know something is lexicographic, okay? So lexicographic is nice for modeling as well and so on, but it's not really something that has behavioral implications beyond, you know, some traditional model, which is surprising, yeah. But so yeah, continuity again is not important behaviorally, but it's going to be important mathematically, because without continuity, it's going to be harder to get a well-defined problem. So we want a model that is well-defined mathematically, okay? So that's also the other part. This is like, you know, you're building your model, right? So you want your model to be well-built. So mathematically it has to make sense. So continuity will help you to do that, okay? But it has no behavioral content. Okay, and then finally, I want to clarify this point. So we showed that a particular utility function represented a preference, right? But does it mean it's the only utility function that can represent that preference? Obviously no, right? For instance, you can easily build another utility function using the upper contour set, okay? Any other idea that you want to use? You know, be my guest, you can do it, right? But in particular, any utility function that is a monotone transformation of the original utility function is also a representation of it. Now, when I said that you don't have completeness, so imagine preferences that are transitive but not complete, the fact that you have multiple utilities means that they are multiple in the sense that they are not monotone transformation of each other, right? So in the example of the COVID case, right? So these are opposite selves almost. The one is cautious, the other is optimistic. So they are not monotone transformations, right? There are some particular pair of alternatives, like going to a patio, which are ranked in opposite rankings, right? So this is not monotone transformation, right? Monotone transformations are only multiple in the cardinal sense. This is the only sense in which they differ, right? The idea that you are monotone transformation means that ranking is preserved. So ranking-wise, these multiple utilities represent the same ordinal information. So in that sense, they are ordinally unique. Do you understand? So you have this uniqueness, the ordinal uniqueness. So now when I said you remove completeness, you actually lose ordinal uniqueness. So you have pair of things that are ranked in opposite sides, okay? So this is the difference, right? So bear in mind. Okay, and finally, utility maximization problem, the UMP. So, okay, so at this stage, we're gonna go practical, okay? So we're gonna assume a lot of things, and then we're gonna get well-defined problems using calculus, okay? So now we're gonna get less picky in terms of behavioral conditions, but we want things to work. So we became pragmatists now, right? So my objective is gonna get a solution to the utility maximization problem, okay? So we assume that preferences are well-behaved. In particular, preferences are rational. What is rational? Complete and transitive, right? Continuous, strictly convex, and locally non-associated, okay? These assumptions imply that the consumer has a utility function that is continuous, and that the consumer, and of course, it's gonna be actually, because it's strictly convex, it's gonna be a strictly quasi-concave, and we're gonna have other properties, and that the consumer, because of local non-association, will satisfy Walras law, okay? For now, I'm even gonna throw you another property out of nowhere, differentiability, right? So nothing in the preference primitives properties that I told you means that the utility is differentiable, okay? So this is too advanced, this is for second year, but you can actually assume that indifference curves are smooth, right? So there is no kinks, and you can describe that mathematically. I'm not gonna do it, right? But I'm just gonna assume directly that utilities are differentiable, okay? And then with that in hand, it turns out that the utility maximization problem produces a solution. And in fact, a unique solution. And this solution is not only unique, but also lives in the budget line, okay? So that's nice. Okay, so the utility maximization problem is written like this: maximize the bundle U of X such that the budget constraint holds. And in fact, I can simplify it to equality. So the utility maximization problem has a solution. Moreover, the solution is unique, okay? So this, you can use what Maria told you, or is gonna teach you. Recall that U is continuous, okay? And the budget constraint is closed and bounded, right? And you can compactify it, in fact, and you can make it close. And then by Weierstrass theorem, we know that a continuous function on a compact set always achieves its maximum, okay? Uniqueness follows from the strict convexity of preferences, and this means U is a strictly quasi-concave, and given that this budget is convex, in fact, here it's just a hyperplane intersected with a positive orthogon. And this is basically a convex set. Then the solution to the maximization problem is also unique, okay? So why do we care? So this is surprisingly simple, but also important. And a lot of your life as practitioner modelers will be that. So you want to model some behavioral phenomenon, right? Like racial segregation in neighborhoods, okay? You write down your utility problem, you write down your constraints. And once you have done it, you actually have to make sure that the problem you pose produces a prediction. What does it mean to produce a prediction? It means that your optimization problem has a solution, right? And also, sometimes you want to make sure, not always, that the prediction you made is unique, okay? And therefore, you need these kind of tools. So what is the trick is that you use continuity and compactness of the budget even it's not linear, right? You understand this, right? So first, imagine your budget now becomes non-linear because you have some taxes, some tax schemes that makes it weird. You have the time of the day, you have only 24 hours, kind of labor, leisure, right? Becomes not convex, becomes, sorry, non-linear, but it still is compact. You still have solutions, right? So I'm gonna show you in a bit with a drawing, but my point is this is beyond linear budget, right? This is a usual tool. And the second thing is about uniqueness. So uniqueness is more delicate. So in particular, in our case, it will work because of convexity of preferences and then linearity of the budget line and local association combined, right? So we're gonna do problem sets trying for you to use this in more general setups. But, and now we're gonna solve this problem. You already did it yesterday, but now we're gonna learn the theory. So already have in mind that what we did. I'm gonna give you a little bit slightly more general because we're gonna consider corner solutions. So yesterday's problem set had only interior solutions. What it means is you didn't have zeros, okay? But in general, you may have utility function that gives you zeros, okay? Or give you corner solutions, okay? So I'm actually gonna give you something to play with for tomorrow. This is not a problem set. I'm gonna give you the example in a bit, but I'm gonna read first these objects, okay? So this is the Karushkin-Tucker conditions. Maria is gonna give you the full generality and theory. I don't need to do that. You write down a Lagrangian. So this you did yesterday. But the extra thing I'm gonna add is the Karushkin-Tucker complementarity or slackness conditions. So first of all, you will notice some differences from what you did yesterday. So most people yesterday did the marginal rate of substitution, right? This marginal rate of substitution can only be done if you have interior solutions, right? Do you understand that? Because if you have zeros, you cannot divide, okay? So this is the conditions for the general case when you have zeros. So in that case, you, instead of having equality of the first order conditions of the Lagrangian, you have inequalities, okay? So it turns out that it holds with equality whenever you have an interior solution, okay? And then if you don't have an interior solution, it can happen with a strict inequality or with equality, okay? So whenever x is 0, then it may be either. So it either is a strict inequality or an equality. So why is that? Let's read the math. So this is just mechanical, right? You derive with respect to xl, the Lagrangian, and you obtain this term. Instead of equating it to 1, you make it less than equal than 0, okay? So it can be either. Now, the slackness condition is gonna tell you the full description of the problem solution. So in parentheses, you have the first order condition, you see? And then you have multiplied by the quantity. So now this is a switch, right? So when xl is 0, what happens? The switch becomes off, right? And now it is inactive. And therefore, this term inside the brackets can be anything. Can be either strictly negative or 0. Do you understand? But if xl is positive, right? Then what happens? The bracket must be 0, right?
Yes.
So that means that the first order condition has to hold with equality. Got it? Okay. So what do you do? So how do you solve this kind of problem? So you actually have to check all cases. So first you try, guess, and verify that x is 0, right? And then you try to solve with inequality, right? And if the inequality doesn't work, right, you get greater than, right? Then it's a no-go. It has to be an interior solution, right? Okay. And then if it's interior, then this thing has to be equal to 0, okay? The bracket. And this is for all L. And finally, because of Walras law, it has to be actually that you have to live in the budget line, okay? So therefore, usually for problems without local association, you also have this bracket condition with lambda, and then lambda will become 0 when the constraint is not binding, okay? So if you have a point inside the budget constraint, then the lambda can be 0. But because of local association, lambda will always be strictly positive. And then the budget line has to be 0. So it has to hit the budget line. Agree? Okay? Good. So, and then of course, for what you did yesterday was the special case. where the interior solution happens, no zeros allowed. So therefore you have the marginal rate of transformation, the substitution, sorry, okay? So I'm gonna give you a problem right now, and then we're gonna get to the properties next class. So I'm gonna give you a quick example. So maximize utility of x that is equal to x1 plus x2 subject to p1 x1 plus p2 x2 equal to that. Okay, so write down the Karushkin-Tucker conditions, please. Okay, so let's do it. So the first thing would be do the Lagrangian, right? So I'm just gonna write it down. And then I have P1 minus W. Okay. And let me obtain the further conditions, right? So with respect to x1, what is it? Is 1, right? And then I have that pretty much here plus lambda b1. And now is less than equal than 0, okay? And the complementarity conditions is that x1 parentheses here usually I think I need a minus here just to simplify. Yeah, this is just changes the value of the Lagrangian, so it doesn't matter. So I can do this thing the same way. So I'm just gonna put a minus here. Yep. Okay, I can do this. So remember that I can just flip it. It's just the value of the Lagrangian. It changes. It doesn't matter. So it's just, I want to write it like this. Both things matter. Both things go the same way. Okay, so now I have this object here. And now I do the same for x2. Just gonna copy it. And then I know this is locally non-associated, yeah. So I know that P1 x2 plus P2 x1's x2 is equal to W, okay? So this is my system, okay? Now how do I solve it? Okay, so I have to check these bracket conditions, right? So I have to say, look, I have here my P1, P2, I derive it is completely linear. So how many cases do I have? I have case 1, right? So I'm gonna check whether, what happens, for instance, if x1 is equal to 0, okay? If x1 is equal to 0, then I can have that this holds, right? So with inequality. Agree?
Yes.
And I'm gonna check at the same time what happens if, for instance, x2, it cannot be equal to 0 because it has to be in the budget line, right? By local non-association. So that case is ruled out. So this has to be strictly greater than 0, right? And in fact, in this case, it's not only that, but actually is that the whole budget set goes to this person. So this is over P2. Do you agree? Because of the budget line, okay? So then I only have this object here. I have that, so this also, because it's positive, it means that now 1 is equal to lambda P2, okay? And now this has to mean, right, by replacing lambda there, that 1 is less than equal than P1 over P2, right? P2, sorry. Which is equivalent to P2 is equal than P1. Okay, agree? So what this is saying that if price of 2 is cheaper than price of 1, because this is full substitutes, right? Then you pick everything x2. Got it? So you could have solved it mentally, right? No, but just that's why I did this example, right? So I did it because you already know the solution. This is a full substitutes case. And of course, if the price of the second good is lower than the price of 1, then I just go all the way, right? So now I go all the way and buy the cheaper one. Got it? So now you can check, of course, the case 2, and you will see that what happens is the opposite, right? When the price of 1 is cheaper than the price of 2, then you buy everything of good 1, okay? And then what happens with equality? Who tells me? What happens when price of 1 is equal to price of 2?
In every S1, S2 on the budget line is
basically you can pick anything, right, that in the budget line, because it coincides with the budget line, right? So anything can happen, okay? So there is something here going on, right? Because what is missing from my theorem? Because my theorem told me that there is a unique solution, and when price of 1 is equal to price of 2, I have infinite solutions. What assumption failed here?
strict on the
Sorry, Brice?
the convexity, the strict quasi-concavity of the utility function.
A strict convexity of preferences, or in the world of utilities, a strict quasi-concavity, right? So it's only weakly concave, weakly quasi-concave, right? So it means that when you have weakly concave, you don't have uniqueness, right? So in convexity, without the strict part, you may have multiple solutions, okay? So this particular case, I'm just gonna tell you the solution, right? When P1 is equal to P2, in fact, you have that X1 actually belongs to the interval 0, W divided by P1, right? And then of course, X2, according to the budget line, will fill in the blanks to hit the budget, right? So any item in this bracket holds, right? And this happens, this is a violation of my theorem because of lack of a strict convexity, okay? And then you can solve the rest. So yeah, basically these tools are useful for any problem, and even beyond this simple case. But you get uniqueness when all these assumptions hold. So for yesterday class, Cobb-Douglas and CES are strictly convex, are continuous, are monotone, in fact, more than locally non-associated, right? So you get all these properties for free, okay? And you're done. Now, when you, in this class, and in particular for the core exams, you will have to deal more often with non-standard, non-interior problems. So yeah, so get used to these Parrish conductor conditions, okay? So practice them and so on, okay? Good. Now I'm gonna keep going, and then the final part is gonna be properties of the demand function, and here we're gonna talk about our properties: homogeneity of degree 0 and the weak axiom of revealed preference. Okay. So homogeneity of degree 0, no Money illusion. Who remembers that condition? No Money illusion. So from chapter 2, you already know it. So who wants to give me a quick recap? So what it means for a demand function to be to satisfy no Money illusion or homogeneity of degree 0?
If the prices and the wealth both like multiply by the same amount, then the bundle that you choose will stay the same.
Oh, perfect. Okay, so now let's prove it, right? So there's the first property we have that Walras law, so that we already proved. Okay, so the second one is homogeneity of degree 0. Okay, so let's prove it. And finally, we have two more properties that I'm going to tell you in a second. The first one is that the weak axiom holds. Okay, surprise, surprise. And the second one is more interesting, is that this Zlotowski matrix has to be symmetric, okay? Which is a big deal. I'm gonna tell you in a bit. But for now, I just want you to check quickly, because right now I didn't do the proof, so I'm gonna do it right now. So I'm gonna prove below the homogeneity that this is homogeneous, okay? So let's prove it, right? So it's very easy to see, right? That the budget set or the budget constraint remains unchanged if I multiply prices by alpha and W by alpha, right? So therefore, if the budget set remains the same, maximizing a preference on the same set has to give me the same answer, okay? And now this person obviously is not falling for money illusion. Now let's think about something, okay? So tomorrow, right? I go to the store, and then you know, I go to Costco and I start purchasing my cart, right? So I put some bread, I put some other stuff and so on. Then I go next week, right? And then the Costco CEO from Wonderland here in London, you know, he increases the cost of bread by 1 cent, okay? Now, who among you will notice that the 1 cent was added to the price of the loaf of bread? So they increase the price by 1 cent. Who among you will notice it? So raise your hands. I mean, my wife notices it, so she's very careful. So she does. I don't. Maybe 10 cents I will, but 1 cent I don't. So if you are like me, you will be fooled by, you know, by this lack of homogeneity, right? Because in particular, I'm actually sensitive. I'm not going to be sensitive to this change, right? So now prices are going to be different, and I'm going to be taking different decisions. So being homogeneous of degree 0 actually requires you to be fully attentive, right? So you know that everything has changed. You know that prices were double and income was double. So why actually there is nominal illusion? Like, you know, there is a macro discussion about this, right? So you increase the amount of money in the economy, right? And then you expect people to spend more, you know, even if in the end, right, you are going to have that prices adjust to the same level, right? And then, you know, you end up in purchasing power as the same as before, but you feel richer, right? So, I mean, that's up to discussion. But a little bit the idea is that you're actually beyond rationality again. So here what is being relaxed is not actually completeness or transitivity, okay? So your preferences are still good. What happens now is that you're relaxing perception. So yet another hidden assumption. So what is the assumption that we're imposing now? And I didn't tell you, right? But I'm telling you now verbally, is that the agent, the consumer, has perfect perception. Do you understand? So you have full attention. So this is a very important working assumption in econ, right? And of course, much of the new theories, new consumer modelers, we are dealing with relaxing that, right? So relaxing full attention, perfect perception. But so an implication of perfect perception is that you are not fooled by this nominal illusion. But in reality, you know, imagine the size of price vectors that you have to have in your mind. So Costco, how many prices do you have there? It's amazing, right? And then, you know, variety, and then you go, and then someone increases 1 cent. You know, this thing increases another cent on this other thing. And then what do, right? So you're gonna change your behavior just because you don't perceive that change, right? So you're gonna be fooled by these changes, and in fact, you're gonna violate this homogeneity. Okay. So what I'm telling you is this even seemingly innocent thing is actually an important implication of this second assumption, which is perfect perception. Okay. So a perfect perception agent, of course, if you multiply everything by alpha and everything by W, this is a huge change of prices. Then this person will notice perfectly, will have all the information, and will maximize like a machine with the correct budget, you see? But in real life, you know, it's harder than that, okay? But so our second assumption is perfect perception, and this is important. Now, the weak axiom and then I'm gonna go to pretty much the part of the Zlotowski matrix. And with that, we're gonna do. So let's prove that. I want you to think about how to prove that a demand function that comes from utility maximization satisfies the weak axiom of revealed preference. And this is also about chapter 2. So this is a lot of information that I'm gonna give you next class, but I want you to see that we're halfway this chapter. It's the biggest chapter we're gonna study. So I just want you to have an extent of what we're still missing. But right now I'm gonna make a stop and just try to prove that the utility thing implies work, okay? So that's what we're gonna do now. So let's do it, okay? So what is warp? So from chapter 2, who tells me in simple words what is warp? Else I'm gonna pick one. So Zach. Can you hear me?
Hello.
Yeah. So can you tell me what is the weak axiom of revealed preference?
Yeah. So from what I gathered, it's basically if a consumer selects a bundle of, say, the good X1 at a certain price, like we assume that that he spends all of his income on that good by Wolver's law. And then further to that, if we notice that there's another consumption bundle that is less than or equal to the wealth or the first consumption bundle that we observed, then we infer that the first consumption bundle is strictly preferred to the second because he was willing to spend all of his income on the first and not on the second.
Okay, and that gives you revelation of preferences, right? You conclude, so I'm gonna tell you in words, right? So if I observe that I have a bundle, right, I'm gonna define a situation where I have two situations, price 1, right, and consumption bundle X1. So these are vectors. And my second situation is P2, right, with consumption bundle X2. So these are two experiments, okay, with different prices. What is the income? Because of Walras law, is just the multiplication of prices and P1 X1 and P2 X2. Okay, so I don't write income. Now, if I observe the following, I observe that P1 X1 is greater than or equal than P1 X2, then I conclude that X1 is directly really preferred to X2. Okay, what Zach said. Now, what is the weak axiom? So the weak axiom, work requires that if X1 is revealed preferred directly to X2, then it cannot happen that X2 is strictly revealed preferred to X1, which is equivalent to saying that it cannot be that P2 X2 is strictly greater than P2 X1. Okay, so you cannot have this strict reversal. Do you agree? So I granted is slightly different from chapter 2, but that's it. So now that's work. Now I want to check that if you have this utility, these bundles X1 and X2 come from utility maximization, right? So what I'm saying is if Xi, right, is the maximizer, okay, of the utility function Ux subject to Pi Xi. This is the multiplication, right? Less than or equal than Pi Xi. This is the income level, right? For I equal to 1, 2. then this data set actually is satisfies warp. Then x1, x2 satisfies warp. Okay, so let's prove it, right? So if I observe, so if proof here, if I observe that the first thing happens here, which is P1, X1. Okay, so this is telling me two pieces of information. First of all, it's telling me that X2 is cheaper than X1 according to price one, so it's in the budget line, inside the budget set, sorry. And second is telling me that X1 was peak, right? So this means that the utility of X1 is greater than or equal than the utility of X2. Do you agree? Yes? Now, assume towards contradiction that you have now that the violation of warp happens. Okay? And this is telling me two pieces of information again, but this means, right, that the utility of X2 is strictly greater than the utility of X1, okay? Do you agree? But this cannot happen, right? But this is a contradiction of the fact that the utility of X1 was above, right? Because this is just the real line again, right? So you cannot have 2 greater than 1 and then 1 greater than 2. It cannot happen, right? So then this is a contradiction, and then I'm done. So you see that now warp follows naturally from utility maximization. What before was this condition that Samuelson invented and said, this is a minimal consistent condition, now is derived from utility maximization. Okay? And it's actually very simple to see why. So warp means that you don't change your preferences in any pairwise comparison. The utility function is way more than that, right? So it requires two things. You don't flip in binary comparisons, but also you don't flip in transitive comparisons, right? So warp is just giving you part of it, which is this asymmetry part. So no cycles of size 2. But in fact, full rationality will tell you that there is no cycles of any size, right? So I'm just going you to show for your entertainment that when there is a unique solution, so this is not tested, but show it, please. So if there is a unique solution to the UMP, right? It follows that if X1 is directly will prefer to X2, and then X2 is directly we will prefer to X3, and ... You have many other revelations until this is directly we will prefer to Xn, right? Then it has to be that X1 is different from Xn, okay? So what is the name of this property? Who remembers that? This property is in chapter 1. It's called acyclicity, right? Okay. So verify this, for fun. I'm gonna do it tomorrow anyway. But so it turns out, and this is the punchline, right? So utility maximization turns out to be stronger than the weak axiom. Okay. So utility maximization implies the weak axiom. But if you have a demand function that satisfies the weak axiom, it may be, in fact, created by something, maximizing something different from a utility function, okay? So, for instance, Shulman asked me about cases where you have complete but non-transitive preferences, right? So you can have complete and non-transitive preferences that are satisfying warp, the weak axiom, okay? But, of course, they're gonna fail acyclicity. So transitivity and completeness will give you acyclicity, okay? And acyclicity, of course, of size 2 is the warp, okay? So acyclicity is a more general form of word. So this also connects triples instead of just comparison of tuples. So proving is actually very simple, so do it at home. And this is rationality. So the punchline is that maximizing a utility is assuming way more than just the weak axiom. So remember the compensated law of demand. Prices goes up, quantities goes down. So rationality implies that, but more. And the question is, do we want this extra baggage or not, right? So I don't think anyone has an issue with the compensated law of demand, right? Prices goes up, quantities goes down, right? Very natural. But what about a cyclicity, right? So think about that. So is that is a feature or is a bug? So you created a new model, right? So this model implies the compensated law of demand, great. But you also got for free a cyclicity. Do you like a cyclicity, right? So think about it, but prove it, okay? So see you tomorrow. Again, the solutions to the problem set of today are uploaded on the GitHub inside I already pushed it. I also did some changes. I think Faye corrected a typo I made. Horrible typo. So in the scalar version of the Zlowski matrix, I mess up the indexes. So in the income part, it said in the scalar version, partial of x k with respect to that w, and it was partial of xl, and then multiplied by xk. So of course, in the matrix version was okay, but in the scalar version, I messed up the indexes. So I corrected it. So if you see the new version that I push in GitHub of the leaks version, is already corrected, okay? So yeah, the good thing about GitHub is that you can see all changes. You can see the track changes. So you can see where I change everything, okay? So download leaks, okay? So I'm gonna be here for 10 minutes and so you can ask me questions. And again, the problem set is not graded. I'm just gonna check that you turn it back, right? And then if you want to be graded, tell me and I'm gonna tell my TA, Shun. So he's gonna grade it for the people that are interested in getting feedback, right? So just send me an email, say who wants to be graded, and then he will do it, okay? And that's good feedback for you. In the real class, of course, you're gonna get a grade, but right now is the summer bootcamp, so it's more optional, okay? So any questions? I'm gonna be here for a while, else you can leave, so don't feel forced to leave, you know, this is your time already. I'm just gonna stay, this is like the after class, you know? So pretend I'm picking my backpack and going to my office. But you know, this creates conversation. But yeah, so yeah, else everyone, you're free to go. So again, it's your time, don't feel committed to stay. I'm gonna stop the recording as well. So guys, do you have any troubles accessing the PDF?
Professor.
Oh,
Yeah.
oh, sorry. Go ahead.